Yesterday, we just talked about, in general, what does it mean for a function to be continuous at a specific number a, and then we talked about what it means then to be continuous from the left or from the right, and then on an interval. So can somebody just recap, if you're saying a function is continuous at a, what does that actually mean? Connor?
The f of a is equal to the limit of as x approaches a.
Yes. So the limit of the function as x approaches a is going to equal f of a, or the actual function value at a. So again, anytime you're really asked to show something is continuous, this is what you're trying to show. Or if something is not continuous, your reasons are either the function value doesn't exist, the limit doesn't exist, or maybe they're not equal to each other if they both do exist. So continuing on with this, today is looking at more specific theorems for combinations of functions and even compositions of functions, how those combinations and compositions can still be considered continuous, and then still going ahead and finding intervals where a function is continuous. And at the very end of yesterday, we had briefly mentioned that determining where a function is continuous is very similar or the same as determining the domain of a function, which we're going to see why in the theorems we're looking at today. So the first theorem, I just numbered the theorems the way they're numbered in the book. And that way, if you're looking at the practice and it says something about theorem 4, it matches in your notes what theorem 4 is. So they just, when they list theorems in a section, it's just kind of theorem 1, theorem 2, theorem 3, unless it has a specific name. So that's all theorem 4 means. But it says if f and g are both continuous at a, and then c is a constant, then the following functions are also continuous at a. So if you're adding two continuous functions, the result is still continuous. Same with subtracting, same with multiplying a continuous function by a constant, same with, oh, this should actually be 4, not number 1 again. But same with multiplying two continuous functions, it's still continuous. And then dividing two continuous functions is continuous as long as g of a is not equal to 0, because that would end up being your denominator. So you are not expected to do proofs in this class, but occasionally I go through proofs of certain things with you because it's still good for you to see why these theorems we have or why certain rules we have are actually true. So you are not expected to mimic a proof on a test, on the AP test, anything like that. But I still think it's important for you to understand why certain things are the way they are. So I could go through a proof of any of these 5 parts. They're all pretty similar. I just want to show you a proof to part 1. So why, if we add two continuous functions, is the result still continuous? So showing the proof of this part, we're starting with, since f and g are both continuous at a, we have, and now we just reviewed what the definition of continuous at a is. So this means if f is continuous at a, we know the limit as x approaches a of f of x is going to equal f of a. And if g is continuous at a, then we know the limit as x approaches a of g of x is equal to g of a. So that's what we know, just knowing that they're continuous. So from here, I'll say therefore, and we are trying to show that f plus g is going to also be continuous, so it's going to fit a similar type of definition. So I'm going to start out by saying the limit as x approaches a of the function f plus g of x. And what I want to show is that this is going to equal the function value f plus g of a, because if it fits that definition, we know it's continuous. I can't just jump straight to there. So from here, I'm using, well, first I'm going to rewrite this function. I know f plus g of x is really f of x plus g of x. So I could write this as the limit as x approaches a of f of x plus g of x. And then I can use limit laws. I know if I have the limit of a sum, that's the sum of the limits. So this would be equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And then from above, based on the fact that f and g are both continuous, I know the values of both of these limits. The limit as x approaches a of f is going to be f of a. The limit as x approaches a of g is g of a. And then I can write f of a plus g of a as f plus g of a. So ultimately, I have shown that the limit as x approaches a of f plus g of x is equal to the function value f plus g of a, using limit laws in between. And then if you ever go on and take higher level math classes where you do have to do proofs, typically you can end proofs with this little square. That means the proof is complete. But again, you're not expected to in this class. So, like I said, you could see how this could easily be rewritten to prove number 2, that f minus g would also be continuous. And then using similar limit laws, we know we have the limit law of a constant times a function. There's a limit law for multiplying and dividing two functions. So hopefully you could see how we could manipulate that proof to fit all 5. But that's just showing why they are also continuous. So then, it says it follows from Theorem 4 and the definition of continuity on an interval that we talked about yesterday, that if f and g are continuous on an interval, then so are those 5 combinations of functions that were in that box above. So this was just showing that these functions are continuous at a number a. This is then putting that together with the definition of continuity on an interval, saying that the continuity would also exist for an interval. And then jumping then to Theorem 5, we have, this is where we start to get into tying this with domains. Any polynomial is continuous everywhere. So that is, it's continuous on its domain, because its domain is all real numbers. So if you know that the function you have is a polynomial, by this theorem, you can say, well, since f is a polynomial, I know it's continuous on this interval. It's continuous everywhere. And then any rational function is continuous wherever it's defined, meaning it's continuous on its domain. So if you found the domain of a rational function, that would also be the interval or intervals where it's continuous.
Wait, where are
Theorems 1, 2, and 3. Yeah, I didn't include all of the theorems. So they would be listed in the section or somewhere in the chapter.
So these are on the
I numbered them the way they're numbered in the book if you need to use them in your practice.
should we know like basically what each theorem is?
You need to know what is stated in the theorems. You don't need to know, like, this is because of Theorem 4. I just put the numbers so that if you're using it in the practice, if they say Theorem 4, you know what theorem they're talking about. So you just need to know, there's a theorem that says these things are true. The theorem itself doesn't have a specific name, so you don't need to know. The book numbered it this way. It's not just Theorem 4 of calculus says this. It's just in the book, that's how it's numbered. All right, so we have, just with this Theorem 5, polynomials, rational functions are continuous on their domains. So example 1 says to use continuity to find this limit. I I just want to kind of show you how using continuity to find the limit is different than just finding the limit. Now, in general, you'll just be finding the limit, but again, to understand how continuity ties to this. Using continuity to find the limit, we would say this expression that's in your limit is your function. So I'm just going to say here f of x is the function x cubed plus 2x squared minus 1 all over 5 minus 3x. What type of function would you say this is? It's rational. It has a polynomial in the numerator and the denominator, so it's a rational function. So I know if f of x is a rational function, it's continuous on its domain. So I can find where it's continuous. So I'll just put here is continuous on its domain. And then I'll list the domain there. How do you find the domain of this function or of a rational function? Yep, denominator can't equal 0, so set it equal to 0 to figure out what x can't equal. So I know 5 minus 3x cannot be 0. It means it is continuous, but not everywhere, so we're finding where it isn't continuous. So we're going to list the intervals where it is continuous. So, and that's why I said here, by this theorem above, it is a rational function, so it is continuous on its domain. So we're just finding that domain. So if I solve this for x, subtract 5 from each side, so negative 3x cannot equal negative 5, and then divide by negative 3, so x can't equal 5/3. Meaning this function is continuous everywhere except when x is equal to 5/3. So I could write that in interval notation as the intervals from negative infinity to 5/3, not included, union the interval 5/3 to infinity. Now, again, going back to the original problem, it says use continuity to find the limit. This part is just showing where the function is continuous. So when I look at the limit and I see the x value is approaching -2, -2 is in the domain, meaning I can evaluate the limit. So I've shown where it's continuous, meaning it is continuous at -2. So I can now go ahead and find the limit. Using direct substitution. So because -2 is in the domain or is within the intervals of continuity, I know direct substitution will work. So I know this is going to equal, if I just substitute -2 in, it'll equal the function value, if that makes sense. Do you have a question for me?
So when it's on the graph and I don't exactly know where the value is, should I just guess?
Estimate, yeah. Yeah.
So more than if I guess and my estimation's going off, I'll get it wrong.
No, if it's not an exact value, as long as you're not like super far off, then you're fine. All right, so in doing this, I know, well, here, let me say this below. So this is what I know by using the continuity. I know that the limit as x approaches -2 of the function will equal the function value at -2. So this is basically telling me direct substitution will work, like I had explained before. So if I substitute -2 in for x, then I'll have -2 cubed, so -8, plus 2 times -2 squared, which is 4, so plus 8 minus 1, over 5 minus, and then 3 times -2 is -6, so really 5 plus 6. So the limit would be -1/11. Here you don't, because you are directly substituting the value in. If this so this is telling us that if I substitute this in, I'm not going to get 0 over 0. That's what finding this was. So if I did get 0 over 0, first of all, that would mean that this value was not in the domain, but then if I had to rewrite this by factoring or anything like that, then I would have to say the limit again and the new expression that I have.
Yeah,
But once you're plugging the number in, you don't have to write it again.
okay.
Yes.
So is this just kind of like a different way of putting the A in, because this was the question, so we had that for step 2.
Yep.
Is this just an alternative to plugging in and then 0 over 0 and then trying to find the limit?
Well, this is saying when it says use continuity in front, if you had to show the continuity is what's telling you direct substitution will work. So, yes. Yes, so by finding where the function is continuous, I can then see -2 is in the domain, meaning what I said down here, I know that I can just substitute -2 in and I'm going to get a value. So I will not get 0 over 0. That's what the continuity tells you. So it is, I mean, yes, you had this limit before you found it without showing all of this first. The continuity is why that works. So it's kind of 2 parts. I'm showing you how to find where it's continuous, and then that's why the direct substitution is working. Okay, are there other questions on example 1? Okay, so if you are using continuity to find a limit, you're basically showing that the x value you're approaching is in the domain. So you're finding that domain first and then using that to find your limit. Theorem 7, again, it's just named Theorem 7 in the book. It doesn't have a specific name. But this then goes on to say polynomials and rational functions are not the only functions continuous on their domain. The functions we work with are all continuous on their domain. So that's where I was saying if you're asked to find where a function is continuous, it's asking you to find its domain. You have to understand that those 2 questions are the same. You're finding the same thing. So polynomials, rational functions are listed here. Root functions are also listed. So just as a review, this would be if you have the nth root. If your n is even, so if you have an even root, like a square root, 4th root, 6th root, what's the domain? 0 to infinity is 0 included. Yes. You can have the square root of 0. It's just 0. And then if n is odd, so if you have an odd root, sorry, there's really no space there. If n is odd, what did you say? Yep, all real numbers. So your domain is all real numbers. If the root is odd, cube root, 5th root, so on. Trig functions are continuous on their domains. So no, these are not saying these are functions that are continuous everywhere. They're just continuous on their domains. Inverse trig functions are also continuous on their domains. Exponential and logarithmic functions are continuous on their domains. So trig functions and inverse trig, it depends on which ones you have, what the domains are. But what is the domain for every exponential function? All real numbers. And then what about logarithmic? Yep, 0 to infinity is 0 included? No. So remember the domain for logarithmic, that's the range for an exponential. The range for exponential is 0 to infinity, 0 is not included, it's an asymptote, so that's now the domain for logarithmic. All right, so then,
So what types of functions
are not. None that we, well, this is basically, these are all the types of functions we work with. they're all continuous on their domains. So, it's not listing here all, like we had those more general groupings of functions, algebraic and transcendental. So polynomials are algebraic functions, but there's more than just polynomials, so there could be some sort of algebraic function that maybe isn't. But for the functions we work with in class, they're all continuous on their domains. We don't work with any super out there types of functions. So example 2 says, where is the function f of x equals natural log of x plus inverse tangent of x over x squared minus 1? Where is this continuous? Again, when you see this question, I could also ask you, find the domain of f of x. They're asking you the same thing. So we basically just need to find this domain. Now to do that, this also is not a rational function because the top is not a polynomial. So the domain is not just every value except for where the denominator equals 0. We also have to look at the top 2 functions that are being added together. Since this is not a rational function, we're looking at each piece. So I'm first going to pull out the natural log of x. And what would the domain, or where would natural log of x be continuous? What is the domain of natural log? Okay. Yes, so 0 is not included. So logarithmic function. So natural log of x would be continuous on its domain, which is 0 to infinity. 0 not included. Inverse tangent, we haven't talked a ton about inverse trig functions so far. They just kind of pop up here and there. Does anybody know or remember the domain for inverse tangent? Negative pi over 2 to pi over 2 is the range. Because that would be the domain of the tangent piece you're taking to take the inverse. It's not negative 1 to 1. It is all real numbers. Yep. So for tangent, I'll write this up here, that way it's actually on my sheet. For tangent of x, the domain, the piece that you're taking for the domain, you're restricting the domain for the inverse. That domain is negative pi over 2 to pi over 2. And the range of tangents is all real numbers. So then those switch for the inverse function. So now the domain for inverse tangent is all real numbers. The domain would, or the, I don't remember what I just said. The domain for inverse tangent is all real numbers. The range for inverse tangent is negative pi over 2 to pi over 2. Okay, so then on the top, because these two functions are added together, that means for this sum, we have to find the intersection of these two intervals. So what values do they share? So overall, the natural log of x plus the inverse tangent of x is, I'm going to abbreviate continuous here, is continuous on, where these overlap would be just 0 to infinity. And then in the denominator, since x squared minus 1 is a polynomial, this is continuous everywhere. But because it's in the denominator, that denominator can't be 0. So we're starting out with our domain is going to be 0 to infinity for the whole function, excluding any values in that interval that make the denominator 0. So yeah, if I figure out and say, well, this would mean x squared minus 1 can't be 0, so x squared can't equal 1, and we would get x cannot equal positive or negative 1, but negative 1 isn't in that beginning interval anyway, so we can kind of exclude that. So the entire function, I'll just say f of x because it's defined above, is continuous on the interval from 0 to infinity, but excluding 1. So if I were to write that in interval notation, I would have the interval from 0 to 1, 1's not included, union the interval from 1 to infinity. And again, it's important that you understand that that is the domain of f of x. So me asking you to find the domain of that function would be the exact same process. You wouldn't necessarily be using the phrasing it's continuous on, but you'd be finding the same intervals. Questions on that? Okay. I am going to skip over example 3 because this is very similar to the previous two examples. So again, using continuity to evaluate the limit, meaning you're first finding the domain of the function like we had done for example 2, and then showing pi would be in the domain so you can use direct substitution. We can for sure do example 4. And then if we have to finish this up tomorrow, that's okay. So in example 4, looking also at theorem 8, again, it's just called theorem 8 in the book. But this is now getting into limits of composite functions. So it says if f is continuous at some number b, and the limit as x approaches a of g of x is equal to b, then if you have the limit as x approaches a of f of g of x, this is equal to f of b. So in my opinion, where it says in other words, this is easier for me to understand, that if you have the limit as x approaches a of f of g of x, this means you're taking the limit of g and then substituting the result into your function f and finding that value. And this into words is explaining why this is true, or trying to have an understanding if x is close to a, and you're finding the limit of g, so then g of x is close to some value of b, and since f is continuous at b, if g of x is close to b, f of g of x is close to f of b. I realize that's wordy. To me, that's the part to me that makes the most sense. But I will show you an example how to apply this. So in example 4, it says evaluate the limit as x approaches 1 of arc sine of 1 minus square root x over 1 minus x. So note that you have a composite function. We have a function inside of the arc sine function. So I can rewrite this and say this is equal to arc sine of, and just take the limit of what's inside. So I can take the limit as x approaches 1 of 1 minus the square root of x over 1 minus x. Whatever value I get then from that limit, I evaluate arc sine, which is inverse sine, at that value. Yes, so if you were wondering what arc sine is, this is inverse sine. You will see, I should put arc sine of x is inverse sine of x. You will see both notations, or could possibly see both notations on AP. So knowing both, you'll just need to know. So working with this, how do I evaluate this limit? Can I use direct substitution? No. If I do, I mean, I should try it first. But I'm going to get 1 minus 1 over 1 minus 1. So 0 over 0, it's indeterminate. So how do I work with this when I have a square root? Yes. So I have to multiply by the conjugate of the top, which would be 1 plus the square root of x. And I do the same thing on the bottom. So I still have arc sine of, I still have the limit as x approaches 1. I haven't taken a limit yet. And when I would need to FOIL along the top. However, with conjugates, the two middle terms always cancel. So I have 1 times 1, that's 1. And then when I multiply 1 times positive root x and negative root x times 1, they cancel. So then negative root x times positive root x, the square roots would cancel, and I would just have minus x. And then anytime you do this, do not FOIL or distribute in the denominator. Leave it because something will end up canceling. So I have 1 minus x times the quantity 1 plus square root x. And you can then see the 1 minus x's cancel out. So I have arc sine of the limit as x approaches 1 of 1 over 1 plus square root x, which now I can substitute the 1 in for x to get 1 over 1 plus 1, so 1 half. So this is arc sine of 1 half, or inverse sine of 1 half. So remember, when you're evaluating inverse trig functions, this means sine of what angle equals 1 half. Yes, you need to know these from trig, the unit circle, in radians. Anybody remember which angle? I forgot I don't know the hand trick, but it is pi over 6. No, because that's sine is 1 over the square root of 2 at pi 4.